The next area that we're going to look at is how to find volume of a solid object. And there's a method that we're going to use called disks and a related method that uses something called washers. So for sure, we know ways to find area using integrals. We've been doing that for a long time. For example, if we had, say that we had the curve y equals square root of x, and maybe from 0 to 1, we wanted to find the area bounded by that curve and the x-axis. And it would be this area in here. Oops, we don't really want to take that. Yeah, this little area in here. And so this area is just calculated by taking an integral from 0 to 1 of the height of that curve dx. And this always represented taking these little tiny rectangles, an infinite number of them, or approaching infinity, and their width was getting littler and littler. And those rectangles, as we summed them all up, this symbol, the integral symbol, means you're going to sum up a bunch of things and accumulate them. That would count all of the area just with all these little rectangles. So now we're going to take this one step further, and we're going to learn how to calculate volumes. So now we're going to learn to calculate volumes, and we are moving from two-dimensional areas to more of a three-dimensional problem. So this time, say that we had our xy coordinates, and let's take that same curve. So y equals square root of x, and again, we'll just take it to from 0 to 1. We'll look at it. But this time, instead of this two-dimensional area that we want to calculate here, we're going to take this region of area, we're actually going to rotate it around the x-axis. And as we're rotating it, we're going to create a solid object. Okay, so here's another image of that y equals square root of x curve. And we're going to now take this curve and rotate it around the x-axis. So it's going to build all the way around, and we'll just form a solid. And so here's a different view of it. Of course, we're going to take everything inside as being filled in. That doesn't show in this picture, but we're going to take this and create a solid object. And now we're interested in finding the volume of this solid. And just like before when we were creating or finding area for area under a curvy thing, calculus is going to enable us to find the volume of solids that have all sorts of curves in them. Back to our hand-drawn picture, we're going to take this curve and rotate it around the x-axis, and as we do, we'll get this solid object that's thick all the way through. And so we have to start thinking, how could we find the volume of this object? And the key is going to be thinking of cross sections. Like if I cut this right in the middle anywhere along here, what would the cross section of that look like? And just like as if you were going to cut a cross section of a tree, the cross section of a tree is like a circle. This guy is going to have a cross section that's also a circle. And so as long as we cut, parallel to the y-axis, we're getting these cross sections that are essentially circles. And we're going to think about taking an infinite number of these cross sections, here, here, here. Similar to how we took an infinite number of rectangles to add up to calculate area, we're going to take an infinite number of these disks and sum them up along our x-axis from 0 to 1, and that will give us the volume of this object. We'll add up this one. All of these disks are going to accumulate and create this solid object. And so this is where we're going to have some sort of integral. Now, what goes inside the integral, it's a little bit different than just calculating area. So there's just a tiny bit more involved. So up until now, we were finding these two-dimensional areas with integrals. We were calculating area, but now we're stepping into these three-dimensional solid objects, and we're calculating volume. And we've already asked the question, what would a cross-section look like of this object? And this object is going to have a cross-section that's a circle. And we're going to add up infinitely many of these. And get our volume. And essentially our integral will look like, we really want the area of this circle times a certain thickness, and we're going to then sum all of those circles up. So we're going to sum up infinitely many circles from 0 to 1 with a certain thickness, this dx. That represents just this thickness in here. And now we think, what do we want to sum up? The area of that circle. So area of x. We won't always have circles, but in these beginning examples, we will always have these disks. So we're using the disk method. So this is a typical way that we'll see a problem presented. We'll be asked to find the volume of a solid obtained by rotating about the x-axis. So we're always told, what is the axis of rotation? Is it the x-axis, the y-axis, maybe some other random line? So find the volume of the solid obtained by rotating about the x-axis, the region under the curve, y equals square root of x, from x equals 0 to x equals 1. And this is the curve that we were just looking at, but now we're going to actually go ahead and calculate what that volume will be for this curve. So we've got y equals square root of x from 0 to 1, and as we rotate it, it'll come down here also, and it'll create this solid object. And a typical cross-section will look something like this, and we're going to sum those up. So finally we get to think through what should the integral exactly look like. Well, we know that we're summing up from 0 to 1, or maybe it's somewhere in here, a bunch of these cross sections, this one, this one, this one. And so our limits of integration will be from 0 to 1. The thickness is that dx. And now we think of what's the area of this object. It's a circle, so we definitely are thinking pi r squared. And where is so pi is just the constant, but where's the radius of this circle? It's from here to here. This corresponds exactly with the y value. So any circle cross section that we take, the radius will actually just be y. And so we can think that the area of this circle is just pi y squared. But we're taking an integration with respect to x, and so we have to represent y in terms of x. And we do know that y equals square root of x, so we're going to take as the area of that disk pi times the square root of x. That's our y, our radius, squared. So again, each of these pieces is representing different things. This is representing the area of a typical disk, and we have an infinite number of these. This is the width of the disk, of each disk. And then this tells us to add up all the disks from 0 to 1. So honestly, throughout this whole section, what we want to just keep in mind is we're adding up from a starting point to a stopping point, some sort of area. It won't always be circles, but these first examples will be dx. And this is how we're going to find volume. So this integral we'll go ahead and calculate. 0 to 1 pi square root of x squared is just x dx. This equals pi x squared over 2 from 0 to 1. That's pi halves minus 0. So the volume of this object is pi halves. We don't know what the units are. We were never given any units of, length or width or height or whatever. But this is the volume. This number represents the volume of this object. Okay, our next example, we have a slightly curvier curve. Find the volume of the solid obtained by rotating about the x-axis, again, this curve, from x equals 1 to x equals 4. Okay, so here is our curve from 1 to 4 of y equals x squared minus 4x plus 5, and we're going to rotate this curve around the x-axis, and so you can start to think about what that might look like, and we're going to assume that it's solid throughout. So when I generate it here on the computer, it will look hollow, but the object that we're interested in is a solid object that it's thick all the way through. So we start to generate it, and it's going to go around the x-axis and come out the other side, and it's growing like this. Okay, so now we kind of see what this object, this would be a really hard object to find the volume of if we didn't have calculus. There's no really sharp straight edges here. It's just a bunch of curvy stuff. And so this is the object that we're going to find the volume for now. So from 1 to 4, our curve is looking something like this. And we're going to stop right at 1 and stop right at 4. And then we're going to rotate it around the x-axis. And so we'll get more of the same over here, but now it's a three-dimensional object. And thinking about the cross-section in here, again, it's another circle with this thickness. And so now we want to add up from 1 to 4, this pi r squared, that's the area times that's the area of the disk, and then the thickness of the disk is dx. But we really don't want this r squared. We need things in terms of x. So we think about what the r is. The radius of each of these little circles will be the y value of the function. And so instead of r, we're going to take whatever y is right here and square it. And this will represent the area of the circle. And so y is this guy right here. We do need things in terms of x because we're adding up with respect to x. So whereas we really are looking at y r squared or pi r squared or pi y squared, because that's the radius, we'll write everything in terms of x. So it will be pi times y squared, which is x squared minus 4x plus 5 squared. So I'll just ask Desmos to find that integral for me from 1 to 4 of pi times x squared minus 4x plus 5, and we have to square that whole thing. Nope, not like that. How about just like this? And then dx. And so this is it. This is the volume of that object, 49.009. So we're going to let Desmos calculate this, and we've Desmos figured out that it is 49.009. This is the volume of this solid object. We're on our third example, and we need to start rotating around different things. Okay, so here we're asked to find the volume of the solid obtained by rotating the region bounded by y equals 8 and y equals x to the third in the first quadrant. So all of this area here, we're going to rotate about the y-axis. So we finally get the y-axis. Like all of these problems, we definitely want to get a picture of what's happening. So I know that in the first, okay, y equals 8 will be easy to graph. That's just this line up here. So here I have y equals 8, and y equals x to the third looks something like this. But they tell us that we're only interested in it in the first quadrant, so I can just take away all of this here. So it looks like I'm interested in this area right here. This is the first quadrant, and these are the two curves that are bounding this area. We're going to rotate it around the y-axis. So we'll rotate it around this way, and we start getting a solid that looks like this. And so now we need to think about what the cross sections should look like. This time we really aren't going to add things up this way, because that's usually the direction that you're rotating is how you want to add things up. It's more natural to look at cross sections this way, and they will be disks. And so this time our disks have a thickness of dy, because this little thickness is a vertical height. And we have circles again, so a pi r squared will take care of the area of this disk, but this time our radius is not y, but it's x. So all of those things we need to keep track of as we're coming up with our integral. And our integral, we know that we want to add things up vertically, so we're going to take these cross sections like this. And that's different than what we were doing before. So we need this dy. The thickness of each of these cross sections is going to be a little bit of y. And then we have pi r squared. We are going from 0 to 8. That's how we're counting up the disks. So this time our limits of integration have to do with y. The last two examples, they were x's. And we really can't have this r in here. So we're going to take that out, and we think we need the radius of it is x squared, or the radius is x, and then we square that to get the area of the circle. But because we're integrating with respect to y, we need to write this in terms of y. They haven't told us explicitly what x is, but we're just going to solve for it using this. So if y equals x cubed, then x will equal y, the cube root of y, or y to the 1/3, either one. So our integral then becomes y to the 1/3, the cube root of y. We always want to remember to square it. Unfortunately, that is a common error, that we forget to square the radius, pi r squared. And all of the pieces look like they're here. So we have our representative cross section here. It's always a good idea to draw that in so you're sure that you're doing things the right way. And we have our area of that cross section, the height of the cross section, or the thickness. And then we're just adding up infinitely many of them from 0 to 8. We'll go ahead and let Desmos do this calculation also. So take all this to Desmos. I mean, this is a relatively easy one, but we'll let Desmos do it. And we get that this integral has a volume of, this solid has a volume of 60.31. And that's our solution. So in these problems, we want to be sure to draw an accurate picture. We have to make a decision about which way we're going to do the integration. Are we going to do it with respect to x or y? And then we have to make sure that be very meticulous about setting up our integral and making sure all of the pieces are there and in the right places and in the right variables. In our fourth example, we're going to find the volume of the solid obtained by rotating the region bounded by these two curves, y equals the cube root of x and y equals x over 4. So y equals the cube root of x and y equals x to the fourth. Looks like we're missing a fourth there in the first quadrant. And so that's why I've restricted it just to this area here. These curves go other places, but we're just interested in this first quadrant. Okay, so we can kind of see the region of this object, and it's going to be rotated around the y-axis. And this is going to introduce a new thing, because when we rotate this, this area that's bounded, it no longer is, if you think of the cross section as we rotate this, it's no longer a circle. It's something more akin to a washer. So as we rotate it, well, let's look at the computer and see how it looks rotated. Okay, so here are our two curves, y equals the cube root of x and y equals x over 4, and we're going to start rotating those around the y-axis. I haven't generated the solid, but you can kind of see how those two curves together will act as they get rotated around. So now we'll take a look at actually generating the solid as we're going around and around and around. And you can kind of see it being generated there. So definitely a really curvy object that would be hard to find the volume of this if we had to just go off of certain dimensions. But because of calculus, we'll just take some representative slices and add up an infinite number of them, piece of cake, and that integration will give us the volume of this object. Okay, so we're back to the handwritten version of our object, and it's rotating around, so we're getting a three-dimensional object. It is being rotated around here. So we want to start thinking about what those little slices will look like as the rotation has all happened. And these slices essentially are, the blue line is creating this large circle, but then we're taking out of it this orange circle, or the circle that's generated by the orange curve, the y equals cube root of x. So when we generate this solid, it'll be more like the slices, like if we're slicing horizontally, these slices will be like little washers, you know, like washers that you buy in a hardware store type washers. And they're really just, so no longer circles because we have a hole in the middle of it, but still we have this thickness, and this outer radius will be the larger circle. So that's the you know, we'll call it x1, I guess. And then this inner circle will have a radius x2. And that's coming from these different functions. So this is where it becomes just a little bit more difficult to visualize what's happening, but we can still pretty much picture this washer just like a circle, but we got to take out that middle function. So this time the integral, we're going to add them up vertically. So our washers are being added up vertically like this. And this point right here is the point, nope, how about 8, 2? That's where they meet up. And so we know that our y value is going up to 2, from 0 to 2. That's the height. So that's how we're going to count up these washers, 0 to 2. And we know that the thickness of each washer is a little dy. We just have to decide what's going on in here. So we're going to take the area of the outer circle, and we'll calculate that, and then subtract from that the area of the inner circle. The outer circle is being generated by the blue function, the x over 4. So we need the area of that circle will be pi r squared. We're going to figure that. We'll call it r1 squared. And then we're going to subtract the area of the inner circle, r2 squared. So obviously we can't be using r's. We're integrating with respect to y. So this is the same thing as x from the blue, x1 squared. And we can't even really use that. But let's think of it this way for a minute. And then the orange one will be pi times x2 squared. This is the area of our washer. We need things in terms of y, so we're going to take this function here, our blue function, and represent it and solve it for x so that we can write it in terms of y's. And so this says that x equals 4y, just solving for x. And so this x1 right here is 4y. So that's good. We can write it in terms of y, and we have the integral of pi, not x, but 4y squared minus pi, and now we're going to figure out this one here. This is the relationship, but we need to write it. We need to represent x in terms of y, so x will equal, looks like y cubed. So y cubed, but that radius is squared. All of this is the integral with respect to y. We're going from 0 to 2. And we'll take this over to Desmos and calculate this. Let's just double check that all our pieces are here. So we're going from 0 to 2 because our y values are going from 0 to 2. And we're taking the outer circle, the blue circle is that larger area, and that's pi 4y squared, pi r squared. And we're subtracting from that this inner circle here. So pi y cubed squared, this is the radius of that inner circle. We did have to remember to write everything in terms of y. That's how we were adding things up. So we had to go back to the original function and make sure that we were writing the radius in terms of y. This is definitely representing a radius here. And this one also, right here, the y cubed is representing a radius. It's the length of that x value for each of the curves. And when I stick this into Desmos, so on Desmos, I just put the pi outside of the integral because it's in each term, 4y squared minus y cubed, whoops, minus y cubed, and that's going to be squared. These are the two radiuses. And then all of that with a dy. And we get that the volume of that solid that's made up of an infinite number of washers will be 76.595. So 76.595. We're on example 5, and this is our last example for this lesson. We're going to find another volume of a solid generated by rotating the region bounded by y equals x squared minus 2x and y equals x. Okay, so we have these two curves. The new thing here is we're going to go about the line y equals 4. So we're not going about the x-axis or the y-axis, but a totally different line. And so on this problem, one of the really significant tasks is to draw an accurate picture. And we'll draw our xy coordinates, and y equals x is nice and easy. That's just going to be a line like this. Here's our y equals x. And then we could use Desmos to graph this y equals x squared minus 2x. And if we do, we'll find that it's a parabola that looks roughly like this. And these guys importantly meet up at the point, this point right here is the point 3,3. And so the region that we're interested in is, we're going to take all this other stuff off because it's just the region bounded by those two curves, so the finite region. And we're going to rotate it about the line y equals 4. And so this is the somewhat new tricky part. Let's move this all down so that we can get a better picture of what we're rotating around. I'm actually going to shrink this a little bit so that I can have a little more room. And then we'll write in the line that we're rotating around. So we're rotating around, let's see, this is 3,3, so y equals 4 will be a line kind of right about there. So you can see that this region here is going to be rotated around this horizontal line. So now the object is becoming a little more difficult to envision, to picture. And though we may not be able to completely visualize, what this object will look like in the end, the most important thing is to get an accurate sense of what the cross sections will look like, because what we're doing is adding up cross sections. And if we can get an accurate picture of the cross sections, that goes a long way to being able to find the volume of this solid. It's dependent on an infinite number of those cross sections. So let's try to see what this might look like as we're rotating it around this horizontal line. This is going to make a big loop around this, And it's kind of hard to visualize it, but we can start to see it looping around this purple axis, and it's always really 1 unit away from that. This point where they were meeting was the 0.33, and this is the line y equals 4. So we're always seeing it's rotating around. And I haven't generated the solid, but we're looking at the two curves, that region bounded by the two curves, kind of working its way through the path that would generate the solid. We can start to see that the solid is going to have some, it's not going to be disks, it's going to be washers, because we have an outer radius. This red curve is going to be our outer radius, and the blue curve will be an inner radius that we need to subtract off, because that's everything between the blue curve and the purple axis of rotation is not going to be taken into the solid that we're generating. So knowing how important a good picture of our situation is, I'm going to try to mirror this region so that we can get a sense. Obviously this is not, you know, the whole object being rotated around, but here it is originally, and then it's going to rotate, and at its height it will look something like this. So we can start to see that when we generate the solid, the washers that we are going to need to count up are going to have an outer radius of the red curve, which is this this guy right here, y equals x squared minus 2x, and then the blue curve will be the line y equals x. We've rotated it around y equals 4. So our washers look something like this. We have the outer one, and then we're going to subtract from it this inner one. And this is an example where we have to be really careful about what this outer and inner radius are, because it's no longer an x-axis that we're rotating it around. I'm going to start with the easy stuff. I know that I need an integral symbol. That's a good place to start. I know that based on my rotation, I'm going to be counting up disks this way. So my little thickness of the disk is dx. So I know that there's a dx here, which means that I can count my starting and stopping point as x equals 0 to x equals 3. Okay, so these are the easier parts. Now we need to decide. I also know that I'm going to be having a subtraction in here. There's going to be a pi. I'll just take that out right now. And now we really need the radius of the red guy squared minus the radius of the blue guy squared. That's counting up the area with this plus this pi. We are getting the area of an outer radius, and we're going to subtract that inner radius. We just have to figure out what this radius will be. So let's start with the easier of the two radii to calculate. It's this, we need the radius of this part of this inner circle. And the answer is not that it's x. We need this is being, the line that's being used is y equals x, but we want to think about, we have a length of 4, and then we subtract off this height. So 4 minus y, here's 4 minus y. If we were going to take a disk over here, it would be, again, we want this radius in here, this inner radius, and so this will be 4 minus y right here, because we have the full length of 4, and then we're going to subtract off this y. You just want to convince yourself that you truly believe that this inner radius is a length of 4, but then we cut off this y. So 4 minus y. And that's the blue. Oops. So 4 minus y is that inner radius, but of course we're dealing with things in terms of x. So what is y in terms of x? Well, luckily y is x. So this is 4 minus x squared is this guy. Okay, red goes next. So red actually goes very similar to how we were calculating the blue radius. This time we want the radius of this outer circle. And again, we have a whole length of 4 here, but we want to cut off this height of y. So right here, we're taking off the y value. And if we were taking a disk over here, it would be 4 minus this y value. And so we're going to take the radius of this outer ring will be also 4 minus y red, but y is, we need everything in terms of x, and we have what y is in terms of x right here. So y equals x squared minus 2x. So this is 4 minus, not y, but we'll use the expression x squared minus 2x. So we have all our pieces. These were the easy pieces, 0 to 3, dx, the pi is sitting outside. We knew that this was a washer situation, but this is the area that we wanted to subtract off, those circles, and this was the larger area. So larger circle minus the inner circle. And we really had to convince ourselves that this was the radius that we were looking for. Okay, so let's write everything out and calculate it. So the volume is going to equal pi from 0 to 3 of 4 minus x squared minus 2x, and of course we need to square that radius, minus 4 minus x squared. And all of that with respect to x dx. We'll go ahead and let Desmos do this calculation here for us. And that number ends up being 96.13. This was definitely the hardest of the 5 problems, and a good one to look over and convince yourselves. The only thing that would later make this more difficult is a problem where we would rotate. Here we were rotating around this line, but if we had a line that was maybe rotating around a vertical line that wasn't the y-axis, that could be equally difficult. So these are examples that you definitely want to think through and make sure that each part you're convinced of. So let's think through these 5 examples. We started off with 2 fairly basic ones where we're just doing disks and we're integrating with respect to x. That may be the easiest kind because most times the equations of the curves are given to us as a y equals and then some expression of x, which makes it easy to just translate it into an integral. The third example was where we were rotating around the line, the y-axis, and so we were counting things up with dy's instead of dx's for the first time. And this made it just a slightly, there was one extra step where we had to think through, okay, the radius is x this time, so when we write that integral and we're doing it with respect to y, we need to write the radius using y's, and the radius needs to represent x. So we had to do a little bit of manipulation to make sure that happened. This was our first washer problem where we had an outer radius and an inner radius. Nothing was being taken in the middle. It was just the whole area was the outer radius minus the inner radius. And this also was being rotated around the y-axis, so we had to do some manipulation of these equations just to get things written so that the integral, which was going to be a dy integral, could all be, those x radiuses could be represented with y's. And this time we had an integral of an outer radius minus an inner radius here, dy. I think we were going from 0 to 2. This was definitely the most challenging of the 5 problems because we had, for the first time, the nice thing was we were rotating about a horizontal line. That's always a little bit nicer, but rotating around something that's not the x or y axis does introduce kind of a deeper level of complexity because you have to think through, okay, what is this radius? I know it's related to the line y equals x, but the radius is not x, it's 4 minus x, or it's 4 minus this y value, which was x squared minus 2x, I think. And so rotating about a line that is not one of the axes, you have to be very deliberate in what you're letting the radius represent. But then the process is really the same. I mean, essentially every time we're just adding up some areas, and we just have to be somewhat careful about how we're calculating this area. So far we've talked about areas that are circles or disks. We'll see some other ways to compute volumes in future sections, but these 5 are fairly representative, these 2 basic ones, then rotating around a y, and then our washer is where we rotated around the y-axis and rotated around a horizontal line that wasn't an axis. So, all right, good job. Next